Okay, good morning, ladies and gentlemen. This is Professor David J. De Los Reyes. The date for today is November 18, 2024, and the time is 3:36 a.m. It's morning already, November 18. My topic for this morning will be a continuation of one of my long video format discussions on my channel. Long video format, it's a complete syllabus. It's a DC circuit. And we are now, or I am now, on lesson number 21. I am discussing the topics on the computation of current on a part of the circuit by using different theorems. So we are done with the Kirchhoff's voltage law, Kirchhoff's current law. We are done with the Thevenin's theorem, Norton's theorem, and superposition theorem. The topic that I will be discussing tonight is actually a continuation of the so-called superposition theorem. I solved a superposition theorem problem and I want to check the validity of the answer on the superposition theorem by using another theorem, and that will be Norton's theorem. So for this morning, the title of the topic will be Superposition Theorem Problem Fact Check by Norton's Theorem. Okay, let's proceed. For those of you who are not yet watching my channel comprises of long video format discussions. And for your information, I uploaded 10 subjects already. It's a complete syllabus. And what I am discussing now is actually the 8 and 9. The 9th is actually analytic geometry. The 10th is actually this circuit here. So for those of you who are planning to take up engineering, this is for you guys. And for those people or youngsters who are planning to take the SAT or CAT exam, this is a good thing also for you if you watch my channel, because it's not the so-called shortcut method of solution, but at least the concept is there. What is important here in the solution is actually the concept. Okay? You cannot go past the short videos or solving problems on the algebra, trigonometry, and other things without knowing the concept. So if you try to watch my long video format discussions, okay, all the explanations will be there. It's not shortcut, but it is the concept. I don't mind solving a problem the so-called fastest way if I don't know the concept, because what is important is actually the concept. Okay, let's proceed. The subject matter that I will be discussing this morning will be a continuation of my long video format topic. It's a complete syllabus. DC circuit lesson number 21, and the title of the topic will be Superposition Theorem Problem. It's a problem on superposition theorem, and it will be fact checked by Norton's theorem. Let's try to check the validity of the answer, if it is correct or not. And to simplify what I will be discussing, actually I solved the same problem as from previous lesson number 19. So I will be solving lesson number 19. This is the problem on lesson number 19. And I will be presenting a Norton's theorem solution. So as a check to the superposition theorem solution. Because actually the answer using the superposition is actually 1.219 amperes. What is being asked here from lesson number 19 is actually the current passing through the 16 ohm load here. Oh, this is this circuit, right? What is being asked is the current passing through this. And from our previous discussion, lesson number 19, what comes out for the current passing here is 1.219 amperes. So I will try, or we will try to check if this answer is correct or not. Of course, it is correct, but we are checking it. So we will be presenting the Norton solution, and supposed to be the answer will be 1.219 amperes. And I will go to the final answer. The current passing through the 16 ohm load using the Norton theorem, which we will be discussing this morning, is 1.219 amperes. Okay? Okay, let's proceed with the subject matter. The figure for lesson number 21 will be the figure for lesson number 19. If you go back to my channel and watch lesson number 19, this will be the figure for lesson number 19. And what is being asked is the current passing through the 16 ohm load. So for the requirement, find the current passing through the 16 ohm load. Capital letter I with the subscript 16 ohms, meaning the current passing through the 16 ohm load. What will be the value using Norton's theorem? We are fact checking it. Fact checking. Okay. Solution. Step number 1. At least we now know the procedures on how to solve problems using the Norton's theorem. And according to step number 1 under Norton's theorem, we will disconnect the 16 ohm load, the load in which the current is to be known. We will disconnect it and short the terminals. So like what the problem says, okay, I will try to get my cloth eraser. Sorry for that one. Okay, we will short the terminals, or how do you call this, disconnect the 16 ohm load, then we will short the terminals. So according to the concept, okay, we remove the 16 ohm load, then we'll try to short the terminals. So what will come out will be this circuit here. We remove the 16, and there is a shorting wire across this. This is the shorting wire. Right? That's a shorting wire. So we remove the 16 ohm load, then we short the terminals. Short the terminals meaning the resistance for the shorting wire should be equal to 0. Okay, the resistance is equal to 0. This is the shorting wire. It's a perfectly short, so the resistance will be equal to 0. What's next to be done? Disconnect the 16 load and short the terminals. Then this is an additional. Compute for the value of the short circuit current. Okay, we disconnect the 16 ohm load, short the terminals, and compute for the capital letter I with the subscript SC, meaning solve for the short circuit current. To solve for this current here, okay, we must have to compute the value of the current coming from the 24 volt source designated by I1. We must have to compute for the current I sub 2 coming from the 18 volt source. And we will try to compute for I sub 3, the current coming from the 12 volt source, okay, if we try to short the terminals. So there are actually 3 unknowns. And to compute for I1, I2, and I3, that will be an easy one. We will be taking the summation of the voltages considering the I1 loop. If we try to consider the I1 loop, okay, forget I2, no, forget this portion here. So what will come out will be this, okay, it will be the 24, the 1 ohm, this is I1. So if we try to forget for the meantime this portion here in this one, then we try to reconnect this terminal here, this will come out. Right? So that will be the resulting circuit. So we take this loop. We take the summation of the voltages considering this loop. Forget I sub 2 and I sub 3 for the meantime. You just consider this one. Take the summation of the voltages and that will be equal to 0. So what will come out? Plus 24 minus the drop here. The drop here will be the current passing here times the resistance 1 ohm. So this is I sub 1 multiplied by 1. Okay? And what will be the voltage drop across AB? I mark this one as AB. AB. What will be the voltage drop across this? It will be the current passing times the resistance across AB. But the resistance across AB, if it's a perfect short, the resistance will be equal to 0. So if we try to take the voltage across this, that will be I short circuit. This is short circuit. Multiplied by the resistance of the shorting wire will be 0. And they should be equal to 0. So since this is 0, it seems this is gone. It is just something like that. Right? So there is only one unknown. We could compute for I1 now. I1 now will be a 24 over 1. We transpose this 1 over 1. So I sub 1 will be, this is 24 amperes. Okay? If we try to consider the I2 loop, the loop containing I2. So for the meantime, forget I1, we are done with I1, and forget I3. So we'll just consider this loop here. So the loop will be this one. Oh, this is I sub 2. So I sub 2. That's I sub 1, this I sub 2. We are on I2 loop already. So considering this I2 loop, still we will take the summation of the voltages and they should be equal to 0. So plus 18, the voltage drop across the 2 ohm load will be the current passing through it, which is I sub 2 multiplied by 2. And the voltage drop across AB, still the same. It will be the current passing multiplied by the resistance between A and B, but it is 0. So this is I short circuit multiplied by 0. So it seems this portion of the equation will be nothing. Right? So again, there is only one unknown, and that one unknown is actually I sub 2. So I sub 2 will be 18 divided by 2, and that will be 9 amperes. So this is 9 amperes. So this is, sorry for that one, 9 amperes. Okay? Consider the I3 loop. If we try to consider the I3 loop, forget I sub 1, forget I sub 2, just consider this portion here. Right? So the configuration will be this. So this is the loop again. Right? That's why I place I3 loop. Am I still on camera, or my camera is still working? Yeah, it's working. Okay? So if we take the summation of the voltages, considering Kirchhoff's voltage law, a plus 12, minus the voltage drop across this 3 ohm load here. The voltage drop across this 3 ohm load will be the current passing through it, which is I sub 3, multiplied by 3. And the voltage drop across AB, this is still A, this is B. It will still be the product of the short circuit current times the resistance across AB, and it is 0. So this is I short circuit multiplied by 0. So since this is 0, I short circuit, for the meantime we do not know, but since this is 0, it seems this portion of the equation is gone. Right? So the only unknown now will be I sub 3. So I sub 3 will be 12 divided by 3, and that will be 4 amperes. So this is 4 amperes. Okay? So it's an easy matter now to compute for the short circuit current, because the current going out will be I sub 1, I sub 2, and I sub 3. And the current entering the shorted portion is actually I short circuit. So actually, short circuit current will be the summation of I sub 1, I sub 2, and I sub 3. Okay? So I place it there. Short circuit current will be the summation of I sub 1, I sub 2, and I sub 3. because we short the terminals upon removing the 16 ohm load. So whether we like it or not, there will be current coming from the 24, 18, and 12. And according to our computation, it is 24, 9, and 4. So the short circuit current will be the summation of this. So it will be 24 plus 9 plus 4, and that will be 37 amperes. So the short circuit current here will be 37 amperes. Right? That's step number 1. What is step number 2? Short the voltage sources and solve for capital letter R with the subscript Rn, meaning we'll try to short out all the voltage sources. We short them out, right? Then we'll try to compute for the voltage across this, no, resistance across this. And that is actually designated Rn. Norton's open circuit voltage. This in here refers to Norton's. So we short the voltage sources, then we'll try to compute for R sub 0. We try to take our ohmmeter, we place it here after shorting the voltage sources, what will be the value? And if we try to short the 24, 18, and 12, the resulting configuration will be this. Right? What remains will just be simply 1 ohm, 2 ohm, and 3 ohm. And we will try to get our ohmmeter, what will be the reading across this. That's the so-called R sub N, meaning Norton open circuit voltage. Okay? And if we try to compute it, theoretically, they are in parallel, right? So there are 3. So 1 over Rn, the total of these 3 here, should be the reciprocal summation of each individual branch. So this is 1 over 1, 1 over 2, plus 1 over 3. And if we try to take the summation of this one, by using our calculator, this is 1, this is 0.5, this is 0.33, so 1.833. The summation of the right hand side will be 1.833. But that's the reciprocal 1 over R sub N. So R sub N now will be 1 over 1.833, and that will be 0.545 ohms. The smallest resistance here is 1 ohm, and as a concept in parallel circuits, the single equivalent of this one will be a value lesser than the smallest one. And the smallest resistance is actually 1 ohm, so the value that we will be coming out, or we will be computing, will be less than 1 ohm. And what comes out is 0.545 ohms. This is correct. Oh, that's step number 2. And step number 3, draw the Norton's equivalent, okay, and reconnect the 16 ohm load. So, according to the Norton's, if it's in Norton's theorem, the short circuit current should be in parallel with the open circuit voltage. Then we'll try to reconnect the 16 ohm load. Okay? So, the final equation on how to compute for the current passing here will be this equation here. Actually, we could derive this one. I didn't show you the derivation. It was derived from the Norton's concept. If we try to take the product of the current passing here, and the voltage across this one is same as this one, so if we try to take the product of short circuit minus I sub 16 times this, and this should be equal to the voltage drop across this, it will be I sub 16 times 16. And if we try to simplify, this will be the equation. Okay, so it's just a matter of direct substitution now. The short circuit current is 37. The open circuit, Norton's open circuit voltage is 0.545 all over RL, which is 16, plus the Norton's open circuit voltage. So this will be 20.165. This is 0.545. It's almost 1/2, right? So this is 20.165 divided by 16.545. And what comes out is 1.219 amperes. It is same as this one. So our solution on lesson number 19 using superposition theorem, the solution or the answer was correct. And we check its validity by using the Norton's theorem, and still what comes out is 1.219 amperes. Okay, that's it, guys. So for those of you who would like to watch my channel comprises of long video format topics. I uploaded 10 subjects already, complete syllabus. So for those of you who are taking up engineering or plan to take up engineering, I think you could learn something from my channel by watching my long video format topics. And if you want to subscribe to my channel is at youtube.com/@ProfDVJ. If you want to share it, please click share. Good morning from Los Angeles.